so I gave you this model here. It's got polynomial term in it, a fourth degree polynomial. We're interested in the relationship between age and population here. And so I've got, my model is predicting population, and I've got an intercept, beta 0, and then I have 4 coefficients for age corresponding to age squared, age cubed, and age to the 4th. And so what I want you to do is I gave you a table of output from a linear model that included the coefficients for each of these beta coefficients, and I wanted you to write out the equation to predict a change in the population from a change in age from the 25th percentile to the 75th percentile. And so here's that output from the table that shows the estimates, the beta coefficients for each of these. Okay, so the long way to do this, if I were to try to estimate these values, would be to first estimate what the predicted value would be if you were in the 75th percentile. And so, first of all, the 75th percentile we said is 73.5, so I'm going to plug that in. So if I was trying to predict what your value would be if you were in the 75th percentile, I would take this estimate for the intercept, I plug that in, plus your estimate for beta 1. And so this has a negative sign in front of it, and I'm going to multiply that by your value here for the 75th percentile, plus, and now it's going to be b squared because we're dealing with the squared term next. And notice I'm including all of the decimals here, and that's because these beta coefficients, so when you're dealing with polynomials, it's going to be pretty sensitive to the actual values of these coefficients, especially as you're dealing with higher and higher order polynomials, because those higher order polynomials are going to end up with really large numbers, and so the decimal points actually end up mattering. And in fact, when I'm doing this here, even the table that I gave you has some rounding obviously in it, and so this is actually not going to give you the exact same answer as if you had loaded the same data that I was running and basically calculated the predicted values directly from the data set using the full coefficients instead of these slightly rounded ones. But just to point out that rounding becomes really important when you're dealing with polynomials because the values you're multiplying them by end up becoming really large. So then I'm going to add the cubed term for the 75th percentile times the beta coefficient for the cubed term. And finally, the term to the 4th power here times the beta coefficient for that term to the 4th power. So that's my predicted value for folks in the 75th percentile. So I'm saying that if you're in the 75th percentile, we predict that your population is going to be, the population for people in the 75th percentile of age is going to be 374.8628. And so that's based on using the coefficients of this model. And then the next step would be to do the same for the 25th percentile. And so I believe this was 24.5? Let's see. 24.5, yeah. So that's the 25th percentile. So I'm going to make that be my A. And now I'm going to actually, I'm just going to copy and paste because it's going to have the exact same coefficients. But now I'm just going to replace all these B's with A's so I can calculate what my predicted value would be if age was in the 25th percentile. So I can run that, and when I run that, I end up getting 1,007. And so if I wanted to know the difference between these two, if I wanted to know what it would be like, what we would expect if you changed from the 75th percentile to the 25th percentile, I would just do the predicted value for the 75th minus the predicted value for the 25th. And I end up getting this negative 632. And so that would say that a change from the predicted value of the 75th percentile to the 25th percentile yields an expected change in population of 632. All right, so that's how we would do this if we were doing it kind of the long way. But if you noticed, I had to do some copying and pasting there, and this kind of had some repetition. And so as I showed you in the slides, there's actually a way to sort of do this in a shorter way because you can sort of see that you could group terms. And so if instead of writing this in 2 lines, I could write this actually in a single line. So I know I'm subtracting this value here from this value here. And so these 2 intercepts are just going to cancel out because if I have 1,672 in this first equation, and I also have it in the second equation, and I'm subtracting it from the second equation, of course, those are just going to cancel out. And then I can see that I basically have a and b times this 10, and then I have b squared and a squared times this negative 1.14. I have b cubed and a cubed times 0.0216, and I have b to the 4th and a to the 4th times negative 0.0001. And so I can just group those terms. Instead of writing 2 equations, I can do b minus a times this linear coefficient here, so the negative 10.6429, plus, and then I'm going to take b squared minus a squared times this the term for the squared, the coefficient for the squared term, plus b cubed minus a cubed times the coefficient for the cubed term, plus b to the 4th minus a to the 4th times this coefficient of the 4th beta coefficient for that to the 4th. And so you'll notice I get the exact same answer there, and that's exactly what I was hoping. So this second equation is the one I was hoping that you would write out here, and just to give you some intuition into why this works. And so the interpretation of this would be a change from the 75th percentile to the 25th percentile of our predictor age would yield an expected change in our y variable, an expected change in population of negative 632. So when you're dealing with polynomials, these individual beta coefficients are actually not meaningful on their own. They're basically meaningless on their own. The only way they can be interpreted is in terms of a change between 2 values. And so you have to pick a b and an a to change between. And that's because, typically we say a 1 unit increase in x yields whatever change in y. But when you have a polynomial or nonlinear terms in your model, that 1 unit change is going to be different depending on if you're changing from 1 to 2 or from 2 to 3 or from 3 to 4, etc. The actual location matters, which is why you need to pick specific a and b values. And a sensible set of a and b values, if you don't have another reason to pick them, are the 75th percentile and 25th percentile of your x variable. So that's exactly what we did here. Just to demonstrate what I was just saying a second ago, I'm going to plug in a different a and b value. So I'm just going to copy this chunk so you can see what I'm saying. But typically when we're fitting a model, we would say a 1 unit change in x yields whatever change in y. But let's just see why that wouldn't work in this case. And so if I set my b to 2 and my a to 1, so this is a 1 unit change. It's a change from 1 to 2. And so a change from 1 to 2 yields a change in y of negative 13.9. Now let's look at a change from 2 to 3, which is also a 1 unit change. That yields a change in y of 15.9. And let's look at a change from 100 to 101. That yields a change of 8. And so these are all 1 unit changes in our x variable, 1 unit changes in a, or from a to b. But because we're dealing with this model that's nonlinear, 1 unit changes are no longer constant. So if we went to a linear model, for example, if we only included the linear term here, we didn't have any of these quadratic terms or higher level terms. For example, if we were just dealing with this, and this was our change from a to b, then of course a 1 unit change, this is sort of more typical of what we would expect for a regression model that doesn't contain any nonlinear terms. Then a 1 unit change is always going to be the same. So regardless of what that 1 unit was, if it was 1 to 2 or 2 to 3 or 100 to 101, it's always going to be this value because this is always going to be 1 times that value. But the reason why that doesn't happen here is because when we've made a and b, a 1 unit change, this first number will always be 1, but b squared minus a squared is not going to be 1, and b cubed minus a cubed is not going to be 1, and b to the fourth minus a to the fourth is not going to be 1, and in fact, those values are going to be different depending on what the starting value a is and what the next value b is. So hopefully this gave you a little intuition into what's going on in these polynomial models to sort of understand why we can't talk about one unit changes anymore.